In this introduction video to the 9300 sampling oscilloscope, we're going to describe how to use the menu system to acquire data and then to display the data and then to use the internal measurements to fully characterize the physical characteristics of the acquired data. During the video, we will acquire three signals. The first signal will be a RF clock signal and then a random data signal. And during both these acquisitions, the trigger source will be the external system clock. In the third acquisition, no system clock is available, so we're going to have to reconstitute a clock in the clock recovery circuit inside the sampling oscilloscope to reconstitute the clock and provide a trigger source. And in this case, again, the data source will be a random data signal used. For the first data acquisition, we're going to take the system clock from the device under test and connect it to the direct trigger input. The second connection then is the data itself, which is going to be connected to the channel 1 input. This is the default menu system for the oscilloscope display. The most important feature is the red box in the center of this screen, and this has been maximized to display the acquired waveform and for signal analysis. Inside the red box at present are the yellow waveform, which is the clock signal applied to channel 1, and the blue trace, in fact, is the channel 2 input, and there is no signal applied to that. So for this application, I'm going to turn off channel 2 and just display the channel 1 waveform. The first important feature is the auto scale button, and this will automatically select the best vertical resolution to give the most accurate results for measuring this input waveform. The horizontal display has also been set to display 2 cycles of the waveform. To achieve this, the B delay time base has been selected and set to, in this particular case, 1.1 nanoseconds per division. We could display the main time base, the A time base, which is in fact running at, in this case again, 2 nanoseconds per division, which displays many more cycles of the waveform. It's also possible to display both waveforms on time bases at once by using the A plus B feature. And here we see the highlighted in mauve, the B zoom time base. And we can pick this up and position it at any point in the waveform display, and then, having selected an area, use again the B time base to display those particular cycles. There's a second method to achieve the same result, is to use the mouse. And here we can select any particular pulse to be displayed by picking and dragging a box, a zoom box, around the waveform, then clicking inside the box, and then again the B time base will display that particular part of the waveform. More information along the top of the screen about the waveform acquisition. So here we can see the analog bandwidth is 20 gigahertz, and the equivalent sampling rate on this time base setting now is 100 gigasamples per second. And the acquisition record length is 2 kilosamples. And also some information about the display mode. In this case, the display mode is persistence. Along the bottom of the screen are the main oscilloscope menus, and these can be selected with a left mouse click. So, for example, I highlight the trigger box and do a left mouse click. We then get a pop-up menu on the left-hand side of the screen. And here we can see the trigger menu where we can, for example, select the trigger source. So if I select another source, then it's gone untriggered, because we know that in this case we've selected an external direct trigger with a clock signal applied. When we finish setting up the trigger menu, again we can minimize that, and so we can maximize the display for the waveform acquisition. In the display menu, many more waveform display formats are available. So the default one was variable persistence, but also available is the dots mode. Here we can see the raw sample points, and these can be joined together using the vector mode. Also, we have a color grading display, and this gives us more information about the waveform acquisition. So we're going to zoom in on a rising edge, and we can see again where the sample points have been taken for that. So I'm going to zoom the box. So here we can clear the display. Now here we can see some samples building up, and here we can see the color grading value. So green is a few hits, and then over here in white we have many hits. So here we can see the waveform most is in the center, so a lot of yellow hits there. So most of the time the samples are taken in the center, and then we just get the occasional in green extreme value on the edges. You can see the refresh time here, it's saving it for 20 seconds and then starting a new acquisition. Also, we can use the undo button if we wish to return to our original time-base factor. And then again, at that point, we could clear the display. It's possible to increase the record length beyond the 2000 samples if more time accuracy is required. This is available in the acquisition menu. So here we see the default value of 2048. It can be increased as high as 32,000 points in this particular instrument, but there is a trade-off that the longer the record length, the longer it takes to acquire the data. So in this particular case, I'm going to select a 4096 record length. Having set up the signal acquisition, we can now use the onboard measurements to fully characterize this clock signal. These are available in the measurements menu. So here we can see the measurement. I'll turn the measurements on, and we can see there are 18 X parameter time measurements and 17 amplitude measurements. So each measurement can be toggled on and off. So for example, the amplitude measurement. So here we see the amplitude is, in this case, 426 millivolts. And in fact, we've got the define parameters on, so we can actually see where these measurements are made. So we can see the mean top value and the mean bottom value, and it's the difference between these that gives us the mean amplitude measurement. We can turn on up to 10 measurements at once, so we could have 5, for example, time measurements, and similarly we could have up to then 5 amplitude measurements. So this gives us a total of 10. So and we can see all these in the measurements box, and if we select the auto, this will automatically scale the measurements box to display the 10 measurements being updated, as we can see, in real time. More information can be displayed by using the statistics. At this point, I'll just minimize the menu. So here we can see a lot more information about the signals being acquired. We see the total number of waveforms being acquired, the minimum, the maximum value, the mean value, and the standard deviation of each particular measurement. A second measurement technique available is the histogram. This can be used to measure amplitude jitter and time jitter. The pop-up menu, again, we can select the vertical and the horizontal. So this is the vertical. So here we're looking at amplitude jitter, the number of hits. This is the particular box we're doing the measurement over. It can be picked and dragged to any particular part of the waveform, and then it records the number of hits at each point. So here we can see there's a lot of hits at the top of the waveform, so we're getting a peak, and then there's relatively few values on the rising and falling edges, and then again there's a lot of hits at the bottom of the waveform. So if we're doing like a mean value, again, we can use this as the top and bottom reference point. Similarly, in the horizontal, we can use this to measure time jitter. Typically this be across one edge. So here we need to increase the time base to select a particular edge, and then we can pick and drag the measurements box to look over a particular edge and clear the waveform. So here we have a rising edge, so I'll just select one particular crossing edge, and then here we're measuring the histogram on that edge. So here we can look at the histogram data. So again, a lot of information. We can see the number of hits inside the histogram, we can see the peak-to-peak jitter. So this signal has got about 11 picoseconds peak-to-peak jitter, and we also get the standard deviation, the RMS value of 2.2 picoseconds. In this example, I'm going to also monitor the clock signal again on the channel 2 input. Having connected the random data signal to channel 1, we can now see many cycles of the waveform on the display. And remember, the trigger is still connected to the external direct, so we actually can see that the waveform is actually triggered. So I'm going to again use the auto scale facility to again change the vertical scale factor to the best vertical resolution for this particular signal. And now we see the waveform is displaying just one eye. So it's set the time base factor, in fact, to put the rising edge at the 20% point and the falling edge at the 80% point. And again, it's used the B time base, on this case again 329 picoseconds, to achieve this with this particular signal. The reason that this is important for eye diagram is we're going to immediately then use the eye diagram measurements to make measurements of this particular eye opening. So this is a non-return to zero signal, and here we see all the eye measurements. So again, a classic one would be to say measure, for example, the eye height. So here we can see the vertical opening of the eye. Again, we got the annotated, so we can see where the measurement's made. So here we see the channel 1 eye height. In this particular case is 373 millivolts. And the other important eye opening would be the eye width. So again, we're looking for the how much jitter is on this particular signal and how big the eye opening is. So in this case, it's 1.5 nanoseconds is the eye opening. Again, we can go ahead and put many measurements on, so we can measure, for example, full time. So here we're measuring the 20 to 80%, and we could measure 10 to 90. It is available. So again, we see the full time measurement here is 278 picoseconds. And we can add further measurements, so we can measure the frequency, and we can measure the jitter. So here we're measuring the jitter at the eye crossing point. So the peak-to-peak jitter is 60 picoseconds, and again the RMS value is available. So the RMS jitter again at this point is 9.4 picoseconds. Having acquired data from a high-speed serial data link and produced a stable displayed eye, it's possible to perform a mask test against these instruments to give a pre-compliance test. These masks are available under the mask test menu, and many of the standards are available: Sonnet, Ethernet masks, Fibre Channel, PCI Express, InfiniBand, Zowie, and Serial ATA. Indeed, if a standard is not available, it's possible to build a user mask and again save it into the library. This particular signal is a Sonnet, and then we can select the particular data rate. So this particular one is an STM4 signal running at 622 megahertz, and then we can build that particular mask. So here we see the mask to that standard, and further then we can select the align, and it makes sure that the time base factor is set correct then for that particular standard, that the mask and the sweep rate are to the defined standard. And then we can say that this particular example is pre-compliant to this standard. In the final example, only the random data signal is available. So this is going to be connected to a divider, and this is then going to be providing an input to the clock recovery input and also into the channel 1 data input. The random data signal applied to channel 1 obviously has random data points, either high or low, relative to each trigger point, and after enough triggers then we can display an eye. But this particular signal has actually a repeating pattern. It's a pseudo-random repeating pattern, and we can actually use our trigger circuit to trigger on this and provide a triggered display. So under advanced trigger, we have a trigger mode called pattern sync trigger, and this can either take a manual value if we know the repeating pattern length, or can use auto to automatically scan along the waveform and find the repeating pattern. So here we see a synchronized pattern now. And I'm going to take a longer time window to actually see more acquisition samples. And I'm going to change the display mode now to vectors. This will make it clearer. And here we can actually see the repeating pattern. In fact, this is 127 bits. So again, in the advanced trigger, we can see that the pattern length is 127 bits. Now I'm going to change the vertical sensitivity to 200 millivolts and position this at the top of the display. And I'm also going to turn on channel 2 now, which has in fact got that clock signal provided. So I'm going to position that at the bottom of the screen, and then I'm going to zoom in with the faster time base. And here we can actually see the random data signal, and we can see there are clock edges available for each of those. But here, where the data stays low, there's no clock edges. So this is the clock. We're going to have to, in our final example, where we have no clock available, reconstitute this clock from the random data sequence. And this is in fact available in the clock recovery input option. In this third acquisition example, we have again connected the random data signal to the channel 1 input, and immediately we can see the amplitude of it, but it is untriggered because there is no system clock available from the device under test to provide the external direct trigger. So in this case, we're going to have to connect the random data signal via a divider to the clock recovery input. So I'll select the clock recovery trigger input, and now clear the display, and we can see again we have a triggered display and have several eyes available. I'm going to now go to the B delay time base and again clear the display, and again we can see a single eye now from which we can make measurements as before using the eye diagram measurement. So this is again a non-return to zero signal, so a classic measurement where we measure the eye height. So again we can see the eye height of this particular signal, 183 millivolts, and similarly we could measure the eye width measurement to the eye width again, the opening of the eye again 1.5 nanoseconds. So this is a way of again making measurements on a random data signal when no system clock is available. During this introduction video to the 9300 sampling oscilloscope, we saw how to use the menu system to acquire data and then display the data and analyze it using the menu system. During the first two acquisitions of the clock signal and the first random data signal, the system clock from the device under test was available, so we could provide this to a direct trigger input. This instrument would be the 9301, which has direct trigger input, or the 9302 also has this functionality. During the third acquisition, no system clock was available from the device under test, so we had to reconstitute the clock by putting the random data signal via a divider into the clock recovery circuit and reconstituting a clock to provide the trigger to acquire the data. This functionality is available in the 9302 instrument, which has the option of clock recovery.